Have you ever stared at an algebraic equation and just seen a big old jumble of letters and numbers? Well, what if I told you that every single one of those equations is actually telling a story? Today, we're going to learn how to read that language, how to turn those abstract symbols into a visual picture. We're basically turning algebra into art.
So let's just ask the question straight up. An equation like this, it isn't just a math problem to solve. Nope. Think of it as a set of instructions, a recipe for drawing a very specific shape. Every equation has a visual identity, and we're about to become detectives and figure out what it is. All right, so here's our game plan. First, we'll see how to turn those numbers into actual pictures. Then, we'll decode the story of a simple straight line. After that, we're going to get a little wild and explore what happens when equations get curvy. Then, we'll look at functions with split personalities, and finally, we'll figure out how to graph an entire region of possibilities.
Okay, first up, let's cover the most fundamental step of all, translating the symbols in an equation into points on a map. Think of the equation as your treasure map, and the coordinates we're about to find, well, those are the x's that mark the spot.
We'll start with this classic linear equation. This is our first set of instructions. And the rule is super simple. Whatever number you decide to plug in for x, y is going to be 3 times that number plus 4. That's it. That's the whole rule.
So how do we find our points? Easy. We just, we pick some random values for x and see what the equation spits out for y. So if we pop in -2 for x, y becomes -2. If we try 0 for x, y becomes 4. Each one of these pairs of numbers is a single solution to the equation. We call them ordered pairs.
And this is where the magic really happens. Each of those ordered pairs we just found is a coordinate, a precise location on our graph. So if we were to plot all those points, like -2, -2, and -1, 1, and so on, and then connect them all, you start to see the equation's true story emerge. It's a perfectly straight line.
Okay, now that we know how to plot points the long way, let's learn some shortcuts. Because honestly, who wants to make a table every single time, right? Every straight line has a few key features that tell its story much, much faster. We're talking about its intercepts and its slope. So the first key features are the intercepts. Think of them as the most important landmarks on our map. They are literally where our line crosses the main roads, the x and y axes. A lot of the time, if you can just find these 2 points, you can draw the entire line. And finding them is a super simple 2-step process. To find where the line hits the horizontal x-axis, you just set y to 0 and solve the equation. To find where it hits that vertical y-axis, you guessed it, you set x to 0 and solve. It is such a quick and powerful way to anchor your graph. Now, the other defining feature is the slope, and that super common y equals mx plus b format. That m value tells you everything you need to know about the line's character, how steep it is and which way it's going. And here's the cool part. If we look back at our first equation, y equals 3x plus 4, the story was right there the whole time. The slope is 3, and the y-intercept is 4. We could have skipped plotting points entirely.
But of course, not all stories follow a nice, straight path. I mean, let's be real. Life isn't always a straight line, right? Well, neither is algebra. Some equations have twists and turns built right into their DNA. So let's explore what happens when our graphs start to bend.
I really love this definition from Geeks for Geeks because it's just so simple and intuitive. A curve is just any line, straight or bendy, that you can draw in one continuous motion. So, what kind of equation gives us one of those bendy lines?
Let's check this one out. See that little 2 floating above the x? That x squared term? That's our culprit. That's the secret ingredient that's going to make this whole thing curve. Anytime you see a variable squared in an equation like this, you can bet you're not dealing with a straight line anymore. Now here's what's really interesting. When we make our table of points for this one, look what happens. When x is -1, y is 0. But get this, when x is +1, y is also 0. The graph is perfectly symmetrical. This squaring action creates this beautiful mirrored curve that we call a parabola. All right, things are about to get even more interesting. What if a function doesn't follow just one rule for its whole life? You see this in the real world all the time. Think about tax brackets or cell phone plans where the rate changes after you use a certain amount of data. These are called piecewise functions, and they're basically functions with multiple personalities.
Take a look at this one. It's like it has a split personality. For one part of its life, for all the x values that are less than 2, it follows the rule for a straight line. But the moment x hits 2 or more, bam, it switches to a completely different rule, the one for a curve. It's literally two different equations stitched together into one.
So how in the world do we graph something like this? The key is to treat each rule separately inside its own zone. The number 2 is our dividing line. For every single x value to the left of 2, we use the rule for the line. For x equals 2 and everything to the right of it, we switch over and use the rule for the curve. Each equation stays in its own lane. And when you put them both together on the same graph, you get this really unique shape. You've got this straight line, just cruising along, and then it suddenly stops and transforms into a curve. It's one single function, but it's telling a more complex story that has a major plot twist right in the middle.
Okay, for our final section, we're going to shift gears a little bit. So far, y has always been equal to something, which gives us a nice clean line. But what if we're graphing not just a line, but an entire region of possibilities on our map?
This is the big question that gets us into inequalities. Instead of y being exactly equal to something, what if y could be greater than it? Whoa, all of a sudden, we're not talking about a single line of points, we're talking about an entire shaded area of infinite solutions. How do you even begin to draw that?
This table here is basically our cheat sheet, and it all comes down to one little phrase, or equal to. If you just see the symbols for less than or greater than, the boundary number itself isn't included, so we use an open circle. But the second you see that or equal to part, it means the boundary point is part of the solution, so we use a closed filled-in circle. For a 2D graph, this just means a dashed line for an open boundary and a solid line for a closed one.
So let's look at a simple example. On a number line, x is greater than 3 means all the numbers to the right of 3, but not including 3 itself. So we put an open circle on 3 to show that's the boundary line, but you can't stand on the line. Then we just shade everything to the right. Now let's contrast that. If we have x is less than or equal to 2, that or equal to is the game changer. It means 2 itself is a valid solution. So this time we put a closed circle on the number 2. We fill it all the way in, and then we shade all the numbers to the left of it. That solid dot tells us, yep, this point counts. So as you can see, graphing is so much more than just, plotting points. It's about visualization. It's about taking these abstract rules and turning them into lines and curves and entire regions that tell a clear story. So I guess the only question left is, now that you know how to read this secret language of equations, what stories are you going to go out and uncover?